We hear all this buzz about AI, right? Neural networks, complex algorithms, but what's really going on under the hood? What's the secret sauce? Well, that's what we're going to dig into today. We're going to uncover the true engine behind all these incredible AI systems.
Yup, statistics. When you really peel back the layers of even the most advanced machine learning models, what you find isn't just a mountain of code, it's a really powerful toolbox of statistical methods. This is what allows a system to actually learn from data, to spot those hidden patterns, and most importantly, to make predictions we can actually count on. So the big question is, how does this hidden DNA actually work? Well, we're going to decode it together. Think of it in 3 parts. First, we're going to learn how to listen to our data, to hear the story it's trying to tell us. Then, we'll get into the fun part, how models are actually built, using the logic of probability. And finally, we'll tackle the really important bit. How do we know if we can trust these models? We'll look at the tests that separate the real deal from just random noise. Sound good? Let's get started.
All right, first things first. Before you even think about writing a single line of code for a machine learning project, you have to get to know your raw material. You've got to understand the language of your data.
And our first set of tools for this are called descriptive statistics. Honestly, you can think of them as the executive summary for your entire data set. Things like the mean give you the average, the center of gravity. Variance tells you how spread out everything is. Is it all clustered together or all over the place? Then you've got things like skewness, which tells you if your data is kind of lopsided. All these little pieces come together to give you that first crucial snapshot of what you're working with.
Now, data isn't just one big blob. It comes in all sorts of shapes and sizes. You've probably heard of the famous bell curve or the normal distribution. That's what things like human height often look like. But then you might have something totally different, like the number of emails you get in an hour, which might follow what's called a Poisson distribution. The key takeaway here is that recognizing these patterns is so important because it dictates which tools from our statistical toolbox we're going to use.
Okay, and here's a little pro tip for you. Everybody focuses on the middle, the average. But honestly, the real action is usually happening out in the tails, the extreme ends of your data. This is where you spot the weird stuff, the outliers, the anomalies, any major imbalances. Looking at the edges first can save you a ton of headaches down the line.
And this is where we start playing detective. We look at correlation and covariance to figure out how different pieces of our data move together. When your ice cream sales go up, do your sunglasses sales go up too? That's a positive correlation. Understanding these relationships is absolutely vital because it helps us figure out which variables actually matter for our prediction, letting us build smarter, leaner models.
Okay, so we've read the data story. Now let's get to the really cool part, using that story to predict the future. This is where we shift from just describing what happened to actually building models that learn and make decisions.
And you have to get this. Pretty much every machine learning model you could think of, every single one, is built on a foundation of probability. Seriously, from the simplest spam filter in your inbox to those giant language models like transformers that seem to write like a human, at their very core, they're just incredibly sophisticated probability engines.
And these concepts you see here, they're the gears of that engine. Take Bayes' theorem, for instance. It sounds complicated, but the idea is beautiful. It's basically a mathematical way for a model to update its beliefs when it gets new information. It's literally the formula for learning from experience.
But this brings us to what is maybe the central challenge in all of machine learning. It's one thing for a model to be accurate on the data it was trained on. That's easy. The real trick is making it reliable and accurate on brand new data it's never seen before. So, how on earth do you do that?
Well, the answer is all about managing something called the bias-variance trade-off. Think of it like this. A high bias model is too simple. It's underfitting. It's like trying to draw a map of a city with just a straight line. It's going to miss everything. On the other hand, a high variance model is too complex. It's overfitting. It doesn't just learn the pattern, it memorizes every little random bit of noise in the data. And that is incredibly dangerous. Imagine a medical AI that overfits. It might be perfect on its training data, but completely fail in the real world because it learned the reflection on the scanner glass instead of the actual tumor.
So yeah, this is the tightrope we have to walk. We're always searching for that perfect sweet spot, a model that's smart enough to capture the real signal, but not so complex that it gets fooled by the noise. That's the key to building a model that can generalize and be truly useful out in the wild.
Okay, so let's say we've built our model. We've found that sweet spot. The results look good. But how do we know? For real? How can we be sure that our model is actually better and we didn't just get lucky with our particular set of data?
This is where we bring in the heavy hitters, inferential statistics.
This is the part of stats that lets us go from simply describing our little sample of data to making really solid, evidence-backed conclusions about the entire world. It's about testing for truth.
And one of the most powerful and common tools for this is A/B testing. You've definitely heard of it, and trust me, you've been a part of dozens of these tests without even realizing it. Ever notice how a thumbnail on your favorite streaming service changes? That's them, A/B testing to see which image makes more people like you click. They are scientifically proving if version B is better than version A.
And having a strict process for this is everything. It's how we replace, "I think this works better," with "I can prove this works better." You start with a clear hypothesis, you have your control group and your test group, you run the experiment, and then you use things like p-values to see if the result is statistically significant. It's how we know for sure it wasn't just a fluke. Beyond that, we have other awesome techniques like cross-validation and bootstrapping. The basic idea is pretty simple. Instead of just testing your model once, you chop up your data into different pieces and test it over and over and over again on different combinations. This gives you a much more robust and realistic picture of how your model will actually perform when it's out in the real world. And this leads to a really critical insight. That accuracy score you see, let's say 95% accurate, that number isn't set in stone. It's an estimate. It has a margin of error. The truly professional way to think about a model's performance isn't as a single number, but as a range. That gives you a much more honest understanding of what it can and can't do. So let's put all the pieces together. We've talked about describing data, building models, and testing them. Now let's talk about why this statistical DNA is so fundamental to building AI we can actually count on.
Because, look, anyone can run a model through a library and get a result. But really understanding these statistical foundations, that's what separates the amateurs from the pros. It's what allows you to not just build a model, but to interpret its results, to diagnose what's going wrong when it fails, and, crucially, to explain how it works to someone else.
And that really leaves us with the one question that matters most. Your AI spits out an answer. It gives you a prediction. But do you actually understand why? Mastering the statistical DNA, that's what gives you the power to answer that question with confidence. Thanks for digging into this with me.